Okay, so we've just learned about how grammars work, and now we're going to learn about a subset of grammars called regular grammars. We're back in chapter 11, and I just wanted to tell you that we're going to be skipping section 11.3.2, which is a section where they teach us how to turn an NFA into a DFA. And really what I want you to know about this is it's always possible to turn an NFA into a DFA. So if you have an NFA, there is a procedure that you can use that will allow you to turn an NFA into a DFA. So to just take your NFA and convert it into a DFA. But you don't need to know how to do it. On the other hand, it is actually pretty interesting. So if you're interested in it, please go read it. If not, you can skip it. We're also going to skip the subsection of 11.3 that talks about minimum state DFAs. Again, it's interesting. You may want to go read it, but we don't have time to cover it in this class. So the one thing that you should know is that every regular expression has a unique minimum state DFA. So what the heck does that mean? That means that every regular expression has exactly one way to turn it into a DFA with a minimum number of states, right? So all of the DFAs with that many states will be exactly the same, except for, maybe the layout of the states and their names. So let me shrink this, and let me just give you an example. Let's consider the regular expression A star B, okay? The smallest DFA that I think I can make for A star B would look something like this. I have state 1 with a loop on A. I have my B going out there. So state 2 is an next-step state, and if I have any A's or B's, they go to some trash state like that. So I think that's a DFA, and it accepts A star B. And I think that is the smallest one you can do. I don't think you can make a DFA for A star B that has fewer than 3 states, okay? Now, you can, of course, make one that looks a little bit different. So let me show you what I mean. Let me just shrink this down a little bit. There we go. I mean, we can draw this again in a different color. And maybe starts up at the top this time. And we start at state 53. But there's still going to be a loop that loops on A at state 53, right? And we go diagonally upwards on a B to state 4, which is our accept state. And, you know, maybe our trash state is state 1 and it's down here. So the placement of the states is different. And we got an A, B coming out of here. The placement of the states is different. The name of the states is different, but I can't see any other way to draw a DFA with 3 states that accepts A star B, except something that looks like this, right? So that's what this means. So that's the stuff we're skipping, right? Again, useful, interesting, but we're not going to be learning how to do it in our class. But now let's talk about that subset of grammars that are called regular grammar, okay? And you've probably guessed that regular grammars can be used to represent regular languages, but they can't be used to represent languages that are not regular. So here's, for first example, here's a language that's not regular, right? This is going to be kind of our standard, not regular language. Surely I've said this before, A to the N, B to the N, not regular, right? Now we can make a grammar for A to the N, B to the N, right? We've done that before. Let me put this out of the way for a second, right? A grammar for A to the N, B to the N, the same number of A's as B's, right? I mean, when I wrote a to the n, b to the n, that's kind of a shortcut, right? I really mean the language a to the n, b to the n, such that n is an element of the natural numbers, right? And my grammar for a to the n, b to the n is going to be one of these bubbly ones, right? So s goes to ASB, and I can't fit it there, so I'll just do 2, or s goes to lambda, right? That's a to the n, b to the n. So we can definitely create grammars that generate languages that are not regular. So we need to figure out, what do we have to do? How do we have to limit ourselves with how grammars work so that we can have a grammar that only generates a regular language? So here is the formal definition of a regular grammar. We say that a grammar is regular, or it's a regular grammar, if all of our production rules look something like this, where the capital letters are non-terminals and this omega is some non-empty string of terminals. Okay, so we can have a non-terminal going to lambda. We can have a non-terminal going to this omega, some string, right, non-empty string. We can also have a production rule that has a non-terminal going to another non-terminal, right? And we can have a production rule that says we have a non-terminal going to a non-empty string of terminals followed by a non-terminal. So what's special about this that makes it a regular grammar and not just any old grammar, right? There's two key things here. The first is that there's only one non-terminal on the right-hand side, right? So if you look at these, you can have a string of terminals, right? But all of these rules, the only ones that have a non-terminal on the right-hand side are the last two, right? Sorry, and yes, they're the only ones that have a non-terminal on the right-hand side. And furthermore, there's only ever one non-terminal on the right-hand side when there is one. And in addition, if there is a non-terminal and there are any terminals in there, the non-terminal has to be to the far right, right? So if you look here, there's either a non-terminal by itself or a non-terminal that's at the very end, right after the string of terminals, right, the non-empty string of terminals. So this means we can't do that bubbling out trick that we've been doing for making those languages that aren't regular. Okay, so we've talked about these rules that tell you what makes a grammar a regular grammar. Let's look at these examples and see which of these are regular. Well, this first one is not regular because it's got that B in the middle there, right? That capital B, a non-terminal, which is not at the far right of the right-hand side of that production rule. Okay? Let's look at the second one here. Again, it is not a regular grammar, right? It's not a production rule that could be part of a regular grammar because we have two non-terminals there, right? And you can't have two non-terminals in a on the right-hand side or on the left-hand side, for that matter, of a regular grammar of a production rule. This last one, however, looks good. What have we got? We've got a string of terminals followed by a non-terminal, which is just this form. So that's a production rule that's that is of a form that could be part of a regular grammar. Now, one thing I just want to clarify about this last rule here is it's okay for to have something of the form S goes to, say, AS. There's nothing in our rules that says that S and T cannot be the same non-terminal. Our rules just say that S and T have to be non-terminals. So don't be stressed out if you see something like that. That's also part of a regular grammar. Right? And you'll notice that in this example we just did, we have A on the left-hand side and A on the right-hand side as non-terminals. That's okay. There's nothing in our rules, go back a slide, nothing said that S and T cannot be the same non-terminal, right? So this is perfectly legal. Now, it is really important to note that grammars are not unique, right? You can have two different grammars for the same language. We've seen that before, right? And there can be two different regular grammars for the same language too. You shouldn't be surprised by this, right? While we said that there is one minimal state DFA, right? We know that there's a ton of DFAs that recognize the same language, right? So for example, if we look again at that DFA that we had before for A star B, right? Here was our DFA for A star B. We had our start, and we had A looping, and B going to state 2, and then we had our kind of garbage state over here, which had an A, B loop, and that was A, B. So that's that's a minimal state DFA. But what if I added state 4 here, and I said state 4 looks like that? That's another DFA, recognizes the same language, right? Just because you can't get to 4 doesn't mean that you can't have it, right? I mean, you could have, there's state 5, which just loops on itself. Still, all 5 of these states, that's a totally valid DFA. There's nothing that says all our states need to be connected. So that's a completely valid DFA that recognizes the language A star B. So just because there's a single unique minimal state DFA doesn't mean that there's a unique DFA. There's a ton of DFAs. Actually, more than a ton, an infinite number, right? We can keep adding nodes as long as we want to. So let me squidge that down and make this one back to full size. So, you know, we can have two different NFAs for the same language. We can have two different DFAs for the same language. There can be multiple regular expressions for the same language, right? So another regular expression for A star B is B plus A star B, right? So you can have a B on its own, or an A followed by 0 or more A's followed by a B. I mean, that's a regular expression. Another regular expression for the same language is just B plus A star B, right? Because it doesn't make a difference if we repeat something, right? These are all perfectly reasonable. And the whole point of this slide is just to tell you that grammars are not unique. There can be two different grammars for the same language, so don't get stuck on that. There can be two different grammars for the same language, and there can be two different regular grammars for the same language as well. So let's see what happens. Does this shrink everybody now? Yeah. Woohoo! So let me just show you two grammars for the regular expression A star B. Okay? Here's one grammar, a regular grammar for A star B, which would be S goes to AS, and S goes to B, right? So as many A's as you want, and then you end with a B. And of course, this language, these production rules here that I've just circled, that's exactly the same as saying it in one line, right? S goes to AS or B, just to remind you we can do it in one line. But we can do this same rule, let's change colors. We can do this same, we can do this same grammar, so we can represent the language A star B with a different grammar. We could say that S goes to AS or AAS or B, right? It's certainly a different grammar, different production rules, right? This one has 3 production rules. The previous one has 2 production rules. The purple one has 2 production rules. And this just says you get to choose when you add your A's. You can add 1 A at a time. You can add 2 A's at a time. Both of them represent the language A star B. And my reminder was ahead of time. Just remember that this notation here is just a shorthand, right? Computer scientists like shorthands. Apparently people who write books about discrete math like using this bar symbol to represent everything from size of to our such that, you know, in a set x such that blah blah blah. So other than the fact that we use that bar symbol for just about everything we can think of, it's important to remember that we're just using a shorthand here. So all I'm just trying to say is if you have a rule that looks like that, oops, I'm not circling it very well, you just want to think in your head, oh, that's shorthand for these three rules, right? Just remember that. Now, one thing that gets harder when we have regular grammars is concatenating two grammars together. So suppose that we have one grammar for A star, right? And this, in fact, is a grammar for A star. And we have another grammar for B star. And there's my grammar for B star. If you're just talking grammars, not regular grammars, then our concatenation rule for grammars, remember that whole business with if one of them starts with S1 and one starts with S2, in this case we're starting with A and B, but that's okay. Traditionally what our rule would have been was we just say S goes to AB, and that would mean, you know, first you have the A's, the A rule, then you have the B rule, so that would be the language A star B star, which is great, except that this rule is not a regular production rule, right? We can't do that. So if you want to concatenate two grammars, it's a problem. Now, this production rule here is not part of a regular grammar, but I just used a regular expression to describe this language, right? The language we're talking about is A star B star, and that's a regular expression, which means the language is regular. So maybe it's no surprise. We can represent a regular language with a grammar that's not regular, but I want to find a way to represent this language, A star B star, with a regular grammar. So, right, that's what this slide says, A star B star is regular. So there's gonna be a regular grammar for it, it's just harder to find. So you may want to pause this video for a minute just to see if you can figure out a regular grammar for A star B star. My hint is work on it from left to right, but now let me just show you. So here's my regular grammar for A star B star. I'm going to say that A goes to little a big A, or B, where B is another non-terminal. Right? That represents two production rules, both of which meet the rules for regular grammars. I'm going to say B goes to little b big B, or lambda. So that's a pair of production rules. No, I'm sorry, that's four production rules, right? Because these ones actually expand. These are shorthand. But I believe that these four production rules will generate the language A star B star, right? But it is a regular grammar, not, well, it is a regular grammar and a general grammar, whereas the previous grammar we were looking at wasn't regular. I'm also going to point out that for this example, I wanted to start with something that was not S, because we're always starting with S. And I wanted to show you an example of something that doesn't start with S. Remember, our rule is that the first production on top is the one that you start with. So in this case, if we were to expand these rules, it really is A goes to little a big A goes to B goes to little b big B, B goes to lambda. So if we just give the production rules and we're not actually giving the full for tuple for our grammar, we say that our start symbol for this grammar is A, right? Because A appears here on the left side of the first rule. So here's another regular grammar problem. We want to find a regular grammar for the language A star, B, C star, D. Again, you know, my hint is just to work from left to right. It's very similar to what we did before. You may want to pause the video and try and figure it out. I'm going to do it for you right now. So let's see, I'm going to start with S for a change, or to get back to normal. And I'm going to say, let's see, S can be little as, or it can go to, and what I'm going to do is I'm just going to say it can go to the rest of this stuff, right? And I'm going to call the rest of this stuff B, right? And the rest of this stuff is just B. And I guess B is going to go to a little b followed by a C, where I'll call C this rest of the stuff. And to do the C part, well, now I'm just trying to do C star D, so C goes to little c, big C, or we could end with a D, right? All right, here's some regular grammar problems from the book. Find a regular grammar for each of the following regular expressions. So let's see if I circle these. So we'll start with A plus BC. Again, consider pausing the video and doing all of these, or pause the video in between them so that you get some practice. But for A plus BC, I'm just going to say S goes to A or BC. Trivial, right? The next one is AB star plus C. So one option is S could just go to C, right? The other option is S could go to an A followed by the rest of it, which I guess I'll call A. And that A rule is going to have to represent my B star part, so I'm going to say A goes to, let's see, it could go to a BA or lambda. All right, so that's that stuff. Let's pick another color. I don't have that many good colors in here, unfortunately. Let's do the next one in black. So now what I'm going to do is I'm going to do this language here. Oops, I just overwrote it. Which is A star BC plus AC. So let's see. For starters, I could just say S goes to AC, right? Because that's the easy one. And now I need to do the rule for A star BC, so S goes to AS or B. And let's see. And in fact, I could write S goes to AS or little b, big B if I'm feeling lazy, right? And then big B goes to C, big B, or lambda. I think that does that one. And we'll do the last one in red. Ooh, there's a concatenation. So you got to start with an AA or a BB. And then you have to end with AA or BB star. I see. So for this one, it's you have to have at least one AA or a BB, and then as many more of them as you like, right? But you can flip back and forth between them. So this one's a little tricky. Even if you didn't pause for the other ones, pause for a minute. So let's see. Instead of starting with S, let's start with Q for a change. So Q could go to AAQ or BBQ. And really, that's going to give us as many pairs of A's or pairs of B's as we want. Because remember, what do we got here? You have to have at least one AA or one BB, and then you follow that with 0 or more of whichever you like. So the trick here is going to be ending. We can't say Q goes to lambda, right, as another rule, because that would mean that that lambda would be in our language, right? We can't have lambda in our language, so that's not a rule we can have. So what we need to do here is we need to say, when you're kind of done with making as many extras as you want, make sure that Q goes to either an AA or a BB. And again, let me just remind you that all of this stuff, this is actually 4 production rules, right? So my production rules for this are Q goes to AAQ, Q goes to BBQ, Q goes to AA, and Q goes to BB. So this thing in here, just a shorthand for these rules. All right, some more problems from the book. Let's slide this up a little bit. Find a regular grammar for each of these. So we'll start with purple. This one's easy, right? This is just a finite number of strings, right? So we could say, you know, maybe I'll start with A here, and I'll say A goes to AA or AB or AC. The next one, let's see, what have we got? We have, it looks like what we have here is odd numbers of A's, right? So you can have 1, 3, 5, or A to the 2n plus 1. So if n was 3, let's see, if n is 0, then it's A to the 1. If n is 1, it's A to the 3. If n is 2, it's A to the 5, right? So this is kind of odd numbers of A's, right? So let's think about how we would do that. In fact, pause the video for a minute. Think about how you do that. And the way I think about this one is it seems to me that you have to kind of always put down pairs of A's until the end when you have to put down a single A. So I'm going to have this set of production rules start with B, just because I want to show you that production rules can start with whatever the heck you want. So I'm going to say it could go to 2 A's followed by a B, or just a single A. And I think if you look at that, you'll see that that'll generate our whole language. This next one, its bark is actually worse than its bite. It looks kind of nasty, right? It's A to the N union B to the N union C to the N, right? The regular expression for this would be A star plus B star plus C star, right? And you should be able to do that in your head, right? You should be able to look at this and say, oh yeah, that's what this is. So what I'm going to do, let's start with capital D now. I'm just skipping C because lowercase c and uppercase c is hard to distinguish sometimes. So, so I'm going to do it with, I'm going to have my first production rule start with D. And what I'm going to do is I'm just going to, since this is 3 different sets of strings we need to generate, I'm going to say D goes to E or F or G. Now remember, that's perfectly legal, that's regular, because this is actually a shorthand for 3 different production rules, right? And now, it's not too bad, right? E is going to be my A, so E goes to AE or lambda, and F goes to BF or lambda, and G goes to CG or lambda. Okay? And so now we just have to do that last one. I guess we'll switch back to purple again. So we're doing this last one. A to the 2k such that k is an element of n, unioned with B to the 2k plus 1 such that k is an element of n. Ouch, right? So what have we got here? Think about it for a minute. Pause for a second and think about what is the regular expression, right? What have we got here? So on the left, this piece here on the left is pairs of A's, right? So it's going to be AA star. And the one on the right is odd numbers of B's. So, you know, K starts at 0, and then we have 1 B, or k is, if k is 1, then we have 3 b's. So I'm going to say it is bb star b, right? And so again, let's see, we were up to G. So let's start this set of production rules with H. And I'm going to take each of these two sides in turn. We'll start with this left one. I is a weird capital letter too, so we'll go to J or K. And we'll do that AA star for the J part. So J is going to go to pairs of A's followed by a J or lambda. And K, which is the other one, is going to go to pairs of B's followed by a K, or in this case not lambda, but we end with a B, so we get that odd number. And finally, we have some even more tricky problems from the book, right? So find a regular grammar for each of the following languages over the alphabet A, B. So strings that have a length that is a multiple of 3, and strings that have an odd number of A's. So pause the video and think about the first one for a minute. We'll do the first one in purple. So pause the video for a minute, think about it. So it helps me to think about the regular expression that represents these things. And a length that's a multiple of 3 means that we're going to have to put down chunks of A's and B's where there are 3 of them. And the easiest way that I can think of for a chunk of A's and B's with 3 is to just kind of list them all out. So we got AAA, or AAB, or ABA, or ABB, or BAA, or, wow, there's a lot of these, huh? BAB, or BBA, or BBB. Did we get them all? It should be 2 cubed, which is 8, right? Because there's 2 possibilities for each space. So 1, 2, 3, 4, 5, 6, 7, 8. Woohoo! I think we got them all. So that's the a regular expression if we just wanted one triple of letters, but I want multiples of triples of letters, right? And 0 is also multiple, so I want 0 or more of these. And so the regular expression I'm going to use, and just pretend this is all on one line, all right, is this thing starred, right? So so how do we do that as a grammar? Well, it's going to be messy, but it's okay. We could say something like S goes to AAAS, or AABS, or ABAS, or ABBS. Let's start again. S goes to BAAS, or BABS, or BBAS, or BBBS. And that gives us the as many as we want, and then we just have to add an or lambda so that we can stop, right? And we have a string when we're done, and also we can have lambda, right? Because lambda is a length that's a multiple of 3, I think. So it's a bit ambiguous, isn't it? I suppose you could argue that it's not a multiple of 3. If you don't think 0 is a multiple of 3, then what you would have to do is you would have to say, all right, scratch that lambda, and I have to end with one of these guys again, so AAA, or AAB, or ABA, or ABB, or BAA, or BAB, or BBA, or BBB. I fit them all in. So you decide. If the language we're talking about is this one that I wrote up here, this regular expression with the star, then you want to get rid of this last line and include lambda. And if you want to have multiples of 3 where there's at least, 3 there, you're starting with 3, then you get rid of lambda and you include all that stuff. Okay, so that's the first one. Now let's see if I can shrink that. Actually, I think it's messy enough that I'm just going to erase it all. Bear with me. Oops. Now we got to erase this piece. There we go. Very good. Okay, so now let's do in blue all strings that have an odd number of A's. And again, pause this for a second. So this is over the alphabet A, B, remember. So we can have as many B's as we want, but whenever we have an A, it's got to be an odd number of A's. So this one's a little bit weird. It would be, I don't know if it would actually be easier if we were trying to do a grammar that wasn't a regular grammar. But here's what I'm going to think about it. We have to build the string up somehow, right? And at any point in time, that string is going to either have an even number of A's or an odd number of A's. And I'm only going to stop when I get an odd number of A's. Okay? When I can only let myself stop generating the string when I have an odd number of A's. So what I'm going to do is I'm going to say that we can start when we have our first production rule. 0 is even, right? So we're going to start. I'm going to have two production rules that I'm going to, let me put it up here in the corner just so I'll do it in green. I'm going to have E represent, I currently have an even number of A's in my string. And I'm going to have D, because I don't like using O as a production rule as a capital letter, to represent I have an odd, right, number of A's. So if I start, I can either start with an A and immediately go into my deal with the fact that I have an odd number of A's now, or I can go straight to the even rule because I have an even number of A's. So if I have an odd number of A's, I have two choices. One, well, let's see, I have several choices actually. One is I could stop, right? I could just throw in a lambda because I have an odd number of A's. Another option is I could add in as many B's as I want, right? Because nobody said anything about the B's. And finally, if I want to add in an A, that's totally fine, but then I kind of go to the world where I now have an even number of A's. And so now we just need to finish off. If I have an even number of A's, I can add B's if I want, right? Or I can add a single A and say now I have an odd number of A's, and so I go back to that kind of odd generating rule. But I can't add the lambda here because I don't want to end with an even number of A's. So I think that's my answer. So again, go away, practice generating these grammars, more problems from the book, more problems that you make up yourself, more problems that other people suggest. Okay, and of course all the homework problems. But that's it for regular grammars. There's not a whole lot to them once you know the rules.